အားလုံးမင်္ဂလာပါအမှန်မှန်တော့ LS တို့ဒီဟာကခန်းအကယ်ဒမီဟာလုပ်နေတာပေါ့နော်အခုတော့7 ရောက်နေပြီလေဆိုမင်းရဆိုရင် beta နဲ့ပတ်သက်ပြောရတယ်နော် basic beta တွေပိုင်းနဲ့ပတ်သက်နည်းနည်းပြောပါရလားမင်းရပါအောင်ပြောပါလေsubspace အကြောင်းပြောရတယ်ပြီးတော့ beta တွေအကြောင်းပြောရတယ်ပေါ့နော်ဒီ basis အကြောင်းတွေပြောရတယ်ဒီနေ့ဒီဟာလေးသွားမယ်ပေါ့နော်ဒီ dot product နဲ့ပတ်သက်ပြီးသွားကြမယ်ပေါ့နော်ကြည့်ရအောင် okay โอเคခဏနော်တခြားလူတွေလာအတန်လေးထွက်နေမြှုပ်လိုက်ပါပြီလို့ okay ဟုတ်ကဲ့ပါစအောင်နော်ဒီဟာလေး7 minute ပါပဲလို့သူကဒီမှာအခုတော့ဒီဟာတော့ရှင်းတော့ရှင်းပါပါအရင်ချုပ်တဲ့ဟာတော့မဟုတ်လားdot product နဲ့ beta length ဆိုတဲ့ဟာလေးပေါ့နော်ဒီဟာအဲ့ဆိုအရင် machine learning မှာလည်းသင်ထားတယ်ပေါ့နော်ဒါပေမဲ့ဒီမှာပို့ပြီးတော့ကိုယ် clear ဖြစ်မှာကြည့်အောင်နော်
A few definitions of operations that we can do with vectors. We've defined addition in the context of vectors, and you've seen that. If you just have two vectors, say a1, a2, all the way down to an, we define the addition of this vector and let's say some other vector, b1, b2, all the way down to bn, as a third vector. If you add these two, we define the addition operation to be a third, you'll result with a third vector, where each of its components are just the sum of the corresponding components of the two vectors you're adding. So it's going to be a1 plus b1, a2 plus b2, all the way down to an plus pn. We knew this, and we've done multiple videos where we use this definition of vector addition. We also know about scalar multiplication. Scalar multiplication. Maybe we should just call it scaling. Multiplication. And that's the case. If look, if I have some real number c, and I multiply it times some vector, a1, a2, all the way down to an, we define scalar multiplication of a vector to be some scalar times this vector will result in essentially this vector where each of its components are multiplied by the scalar, c a1, c a2, all the way down to c an. And so after seeing these two operations, you might be tempted to say, gee, wouldn't it be nice if there was some way to multiply two vectors? This is just a scalar times a vector. You're just scaling it up, and that's actually the actual effect of what it's doing if you visualize it in 3 dimensions or less. It's actually scaling the size of the vector. We even happen to find size very precisely just yet, but you understand at least this operation. For multiplying vectors or taking the product, there's actually 2 ways, and I'm going to define one of them in this video, and that's the dot product. The dot product. And you signify the dot product by saying a dot b. So they borrowed one of the types of multiplication notations that you saw, but you can't write a cross here. That'll be actually a different type of vector multiplication. So the dot product is, it's almost fun to take because it's mathematically pretty straightforward, unlike the cross product, but it's fun to take, and it's interesting because it results, so this is a1, a2, all the way down to an. That vector dot my b vector, b1, b2, all the way down to bn, is going to be equal to the product of each of their corresponding components, so a1, b1, added together, plus a2, b2, plus a3, b3, plus all the way to an, bn. So what is this? Is this a vector? Well, no, this is just a number. This is just going to be a real number. You're just taking the product and adding together a bunch of real numbers. So this is just going to be a scalar, a real scalar. So this is just going to be a scalar right there. So in the dot product, you multiply 2 vectors and you end up with a scalar value. Let me show you a couple of examples just in case this was a little bit too abstract. So let's say that we take the dot product of the vector 2, 5. We're going to dot that with the vector 7, 1. Well, this is just going to be equal to 2 times 7 plus 5 times 1, or 14 plus 6. No, sorry. 14 plus 5, which is equal to 19. So the dot product of this vector and this vector is 19. Let me do one more example, although I think this is a pretty straightforward idea. Let me do it in mauve. Okay, so I have the vector 1, 2, 3, and I'm going to dot that with the vector -2, 0, 5. So it's 1 times -2 plus 2 times 0 plus 3 times 5. So it equals so it's minus 2 plus 0 plus 15. Minus 2 plus 15 is equal to 13. That's the dot product by this definition. Now I'm going to make another definition. I'm going to define the length of a vector. The length of a vector. Length of a vector. And you might say, Sal, I know what the length of something is. I've been measuring things since I was a kid. Why do I have to wait until a college level, or hopefully you are taking this before college maybe, but what is now considered a college level course to have length defined for me? And the answer is because we're abstracting things to well beyond just R3 or just three-dimensional space, what you're used to. We're abstracting that these vectors could have 50 components, and our definition of length will satisfy will work even for these 50 component vectors. And so my definition of length, but it's also going to be consistent with what we know length to be. So my definition, so if I take the length of A, and the notation we use is just these double lines around the vector, the length of my vector A is equal to, this is a definition, it equals the square root of each of the terms, each of my components squared, added up, plus A2 squared plus all the way to plus AN squared. And this is pretty straightforward. If I wanted to take the, this was vector B. If I wanted to take the magnitude of vector B right here, this would be what? This would be the square root of 2 squared plus 5 squared, which is equal to the square root of, what is this? This is 4 plus 25, square root of 29. So that's the length of this vector. And you might say, well, I already knew that. That's from the Pythagorean theorem. If I were to draw my vector B, let me draw it. Those are my axes. My vector B, if I draw it in standard form, looks like this. I go to the right 2, 1, 2, and I go up 5, 1, 2, 3, 4, 5. So it looks like this. My vector B looks like that. And from the Pythagorean theorem, look, if I wanted to figure out the length of this vector in R2, or if I'm drawing it in kind of two-dimensional space, I take this side, which is length 2, I take that side, which is length 5. This is going to be the square root from the Pythagorean theorem of 2 squared plus 5 squared, which is exactly what we did here. So this definition of length is completely consistent with your idea of measuring things in 1, 2, or 3-dimensional space. But what's neat about it is that now we can start thinking about the length of a vector that maybe has 50 components, which, really to visualize it in our traditional way makes no sense. But we can still apply this notion of length and start to maybe abstract beyond what we traditionally associate length with. Now, can we somehow relate length with the dot product? Well, what happens if I dot A with itself? What is A dot A? So that's equal to, I'll just write it out again, A1 all the way down to AN, dotted with A1 all the way down to AN. Well, that's equal to A1 times A1, which is A1 squared, plus A2 times A2, A2 squared, plus all the way down, keep doing that all the way down to AN times AN, which is AN squared. Well, what's this? This is the same thing as the thing you see under the radical. These two things are equivalent. So we could write our definition of length, of vector length, we can write it in terms of the dot product, of our dot product definition. It equals the square root of the vector dotted with itself. Or if we square both sides, we could say that our new length definition squared is equal to the dot product of a vector with itself. And this is a pretty neat, it's almost trivial to actually prove it, but this is a pretty neat outcome, and we're going to use this in future videos. So this is an introduction to what the dot product is, what length is. In the next video, I'm going to show a bunch of properties of it. It'll almost be mundane, but I want to get all those properties out of the way so we can use them in future proofs.
ဟုတ်ပါပြီပြည့်ရလူလေးခဏစားအောင်နော်ကိုတက်ရဲ့မောင်လေးကိုထုတ်ရဲ့ကိုထုတ်ရဲ့တော့တင်များဟုတ်ပါပြီဒီကတော့ trade ဘာမှတော့မဟုတ်ပါဘူးခဏစားအောင်နော်တို့လေးနည်းနည်းတော့ဒီဟာလေးအရင်ဘက်ကလဲဆို machine learning မှာသူ့ဟိုဒီthat နဲ့ပတ်သက်ပြီးနည်းနည်းပြောထားတယ်ပေါ့နော်
အဖေထိုင်ရတယ်
ခဏလေးစားနော်ဟုတ်ကဲ့ပါဒီမှာ trade ထူတော့မဟုတ်ပါဘူးအဓိကသူကဒီဟာကိုဘာကိုပြောရလဲဆိုတော့ဒီ dot product ဆိုတာဘာကိုပြောတာလဲဆိုတာရေပြီးသွားရင် length ကိုဒီ battery ရဲ့ length ကိုဘယ်လိုရှာလဲဆိုတဲ့ဟာလေးနည်းနည်းမရှိရမြင်အောင်ပေါ့နော်ဒီဟာလေးပို့ပြီးရှင်းသွားမယ်ထင်တယ်ဒီဟာအရင်တော့လည်းလို့ရှာတယ်ပေါ့နော် machine learning course မှာလည်းဒီ length နဲ့ပတ်သက်ပြီးသုံးချရတယ်ပေါ့နောက်ပိုင်းဒီ transformation လုပ်တဲ့ခါကျရင်ဘယ်လိုသုံးပါဆို length ကိုသုံးပါရောလားမမိကြလားမသိဘူးအဲ့ဒါလေးလည်းပါတယ်ပေါ့နော်ဒီမှာဆိုရင်သူကပို့ပြီးတော့မရှိတယ်ရှင်းပြသွားသေးတယ် Pythagorean theory ကိုသုံးပြီးတော့ဘယ်လိုလုပ်တယ်ဘာဖြစ်တယ်ညာဖြစ်တယ်ဆိုပြီးတော့ပေါ့နော်ဒီမှာဆိုရင်လည်းဒီမှာဆိုရင်အဓိကကိုကဒီမှာဆိုတော့ formula လေးဘယ်လိုလုပ်လို့ရတယ်ဆိုပြီးတော့သူပြောတယ်ပေါ့နော်ပထမဆုံးတစ်ချက်ကသူကပထမဆုံး proof လုပ်ပြတယ်ဒီမှာဆိုရင်ဒီလိုမျိုးဆိုရင်73ရတဲ့အကြောင်းသူတွက်ပြတယ်ပေါ့နော်ဒီလိုမျိုးရှိတယ်ပြီးသွားရင်နောက်တစ်ခု ls note အရဆိုရင်ပေါ့နော် dot product ကအမြဲတမ်းသူက produce လုပ်တဲ့ခါကျရင် scalar value ကို produce လုပ်ပေးတယ်ပေါ့နော်ဒီဟာကို dot product ရှာတယ်ဆိုရင်သူ့ရဲ့အောက်ခန်းကထွက်လာမယ့် output ကဘာဖြစ်နေမလဲဆိုတော့ scalar value ဖြစ်နေပြီပေါ့နော်အဲ့ဒါလေးတစ်ချက်နောက်ထပ်ကြည့်နေပါတော့နော်နောက်တစ်ခုကဒီကိုယ့်ရဲ့ဒီ battery ရဲ့ length ကိုရှာတဲ့ခါကျရင်ဘယ်လိုတွက်လို့ရလဲဆိုတဲ့အကြောင်းသူပြောထားတယ်ပေါ့နော်ဒီမှာဆိုရင်ဒီ Pythagorean theorem ကိုသုံးပြီးတော့ကိုကတွက်လို့ရတယ်ဆိုတဲ့အကြောင်းလေးပြောထားတယ်ပေါ့နော်အဲ့ဒါဆိုအရင်တော့ဆိုရင်ကျောင်းမှာတော့ဆိုရင်ဒီ Pythagorean theorem လောက dimension တစ်ခုလောက်ဆိုရင်ဘာမှ trade ထူတော့မရှိတယ်မြင်တယ်ပေါ့နော်သူတို့ကပြောရဘာဖြစ်လို့ငါ့ကိုဒီဟာငါငယ်တော့သင်ခဲ့တဲ့ဟာကိုဖြစ်လို့ငါအခုချိန်နေလာပြန်သင်နေတယ်ပေါ့နော်အဲ့ဆိုတော့အဓိကဒီဟာလည်းဒီ abstract ဆိုတာဒီမှာပြောချင်တယ်ဆိုတော့ဒီချုပ်ပြီးပြောလိုက်တာဖြစ်တဲ့အတွက်ကွာလို့ dimension များလာလေကြာရင်ဘယ်လိုမျိုးပြောလို့ရမလဲဆိုတာမျိုးအဓိကရှာရဲဆိုတဲ့သဘောလေးပေါ့နော် formula တစ်ခုရှာရဲဆိုတဲ့သဘောလေးပေါ့ဒီမှာဆိုရင်ဒါ R2 ဆိုရင်ဒါအခုလို့2 dimension ပဲဆိုရင်ဘယ်လိုလုပ်မလဲဒီမှာဆိုရင်ဒီက n က2မကလို့သူကmillion ပဲဖြစ်ထောင်ပဲဖြစ်နေအကုန်လုံးဖြစ်နေပေါ့နော်ဒီလိုမျိုး formula ထပ်သုံးပြီးရှာလို့ရတယ်ဆိုတဲ့အကြောင်းလေးကိုပြောရတယ်ပေါ့နော်ကိုယ် better length ဘယ်လောက်ရှိလဲဆိုတော့သိဖို့အရေးကြီးတယ်ပေါ့နော်ဒီ machine learning မှာဆိုရင်ဒီဟာလေးက length ဘယ်လောက်ရှိလဲဆိုတော့သိဖို့ဒါ attention ဖြစ်နေလိုအပ်တယ်ဆိုတဲ့သဘောလေးကိုလည်းပြောထားပါတယ်လို့ဒီဟာနဲ့ပတ်သက်ပြီးတော့ဒီဟာနဲ့ပတ်သက်ပြီးအဲ့လဲဆို question မေးစရာရှိလားရှင်းကြလားမောင်လေးတို့ညီမလေးတို့
ဟုတ်ကဲ့ရှင်းပါလေ
ဟုတ်ကဲ့ပါအဲ့ဒါနောက်တစ်ခုသွားမယ်နော်ဒီမှာဒါဘာမှ trade လို့မပေါ့ dot product
ရှင်းပါလေ
ဟုတ်ကဲ့ပါ dot product ပတ်သက်တာကိုဘယ်လိုရလဲဆိုတဲ့ဟာရယ်ပြီးသွားရင်ဒီ dot product ကို base လုပ်ပြီးတော့ပေါ့နော်သူအခြေခံပြီးတော့ better length တွေကိုဘယ်လိုရှာလဲဆိုတဲ့အကြောင်းလေးပြောရတယ်ပေါ့နော်အခု ls ပြန်မေးပါနော်တေချာနားလဲရနော်ဟုတ်တယ်ဟုတ်ပြီးရင်ဒီဟာဘယ်လို dot product ကဘာလို့ထုတ်လာလဲဆိုမေးမဖြေနိုင်နော်ရိုက်ပါနော်ခင်ဗျားတို့လေ length ကို dot product ကို base ခံပြီးဘယ်လိုရှာလဲဆိုတဲ့ဟာလေးmessage တင်ပါတယ်ပေါ့နားလဲနားထောင်ပေါ့နော်ဖြစ်နိုင်ဒီနောက်မှာစာချရေးတာဖြစ်ပါဖြစ်ပေါ့နော်ကိုကိုမမိအောင်လုပ်ပါလို့ဟုတ်ပြီလားအခုတော့ခုနကတော့ dot product ရှာတာပေါ့နော်ဒီမှာဆိုရင်ဒီက properties တွေကိုပြောပြမယ်ပေါ့နော်ဒါလေးဒီနားထောင်ရအောင်
This video, I want to prove some of the basic properties of the dot product. And you might find what I'm doing in this video somewhat mundane, and you know, to be frank, it is somewhat mundane, but I'm doing it for two reasons. One is, this is the type of thing that's often asked of you, when you take a linear algebra class, but more importantly, it gives you the appreciation that we really are kind of building up a mathematics of vectors from the ground up, and you really can't assume anything. You really need to prove everything for yourself. So the first thing I want to prove is that the dot product, that when you take the vector dot product, so if I take v dot w, that it's commutative, that the order that I take the dot product doesn't matter. I want to prove to myself that that is equal to w dot v. And so how do we do that? Well, and this is the general pattern for a lot of these vector proofs. Let's just write out the vectors. So v will look like v1, v2, all the way down to vn, say that this is equal to v, and let's say that w is equal to w1, w2, all the way down to wn, all the way down to wn. So what does v dot w equal? V dot w is equal to, I'll switch colors here, v1 times w1, whoops, v1 w1 plus v2 w2 plus all the way to vn wn. Fair enough. Now what does w dot v equal? Well, w dot v, when I made the definition, it's, you just multiply the products, but I'll just do it in the order that they gave it to us. So it equals W1 V1 plus W2 V2 plus all the way to Wn Vn. Now, these are clearly equal to each other, but because if you just match up the first term with the first term, those are clearly equal to each other. V1 W1 is equal to W1 V1, and I can say this now because now we're just dealing with regular numbers. Here we were dealing with vectors, and we were taking this weird type of multiplication called the dot product. But now I can definitely say that these are equal because this is just regular multiplication, and this is just a commutative property. Commutative. Let me see if I'm spelling. Commutative property of multiplication. We learned this in, I don't know when you learned this, in second or third grade. So you know that those are equal, and by the same argument, you know that these two are equal. That you can just rewrite each of these terms just by switching that around. That's just from basic multiplication of scalar numbers, of just regular real numbers. So that's what tells us that these two things are equal, or these two things are equal. So we've proven to ourselves that order doesn't matter when you take the dot product. Now the next thing we could take a look at is whether the dot product exhibits the distributive property. So let me just define another vector x here. Another vector x, and you can imagine how I'm going to define it. x1, x2, all the way down to xn. Now, what I want to see, if the dot product deals with the distributive property the way I would expect it to, then if I were to add v plus w and then multiply that by x, and first of all, it shouldn't matter what order I do that with. I just showed it here. I could do x dot this thing. It shouldn't matter because I just showed you it's commutative. But if the distribution works, then this should be the same thing as v dot x plus w dot x. Right? If these were just numbers, this was just regular multiplication, you would multiply it by each of the terms. And that's what I'm showing here. So let's see if this is true. If this is true for the dot product. So what is v plus w? V plus w is equal to, we just add up each of their corresponding terms. v1 plus w1, v2 plus w2, all the way down to vn plus wn. That's that right there. And then when we dot that with x1, x2, all the way down to xn, what do we get? Well, we get v1 plus w1 times x1 plus v2 plus w2 times x2 plus all the way to vn plus wn times xn. Right? I just took the dot product of these two. I just multiplied corresponding components and then added them all up. That was the dot product. This is v plus w dot x. Let me write that down. This is v plus w dot x. Now, let's work on these things up here. What is v dot, let me write it over here. What is v dot x? V dot x, we've seen this before. This is just v1, x1, no vectors now. These are just their actual components, plus v2, x2, all the way to vn, xn. What is w dot x? W dot x is equal to w1, x1 plus w2, x2, all the way to wn, xn. Now, what do you get when you add these two things? And notice I'm just adding, here I'm adding two scalar quantities. That's a scalar, that's a scalar. We're not doing vector addition anymore. So this is a scalar quantity, and this is a scalar quantity. So what do I get when I add them? So v dot x plus w dot x is equal to v1 x1 plus w1 x1 plus v2 x2 plus w2 x2 all the way to vn xn plus wn xn. I know it's very monotonous, but you can immediately see we're just dealing with regular numbers here. So we can take the x's out, and what do you get? This is equal to, right here. This is equal to, we can just take the x out, factor the x out, v1 plus w1 x1 plus v2 plus w2 x2 all the way to vn plus wn xn. which we see this is the same thing as this thing right here, So we just showed that this expression right here is the same thing as that expression, or that distribution, the distributive property seems to or does apply the way we would expect to the dot product. And I know this is so mundane, why are we doing it? But I'm doing this to show you that we're building things up. We couldn't just assume this, but the proof is pretty straightforward. And in general, I didn't do these proofs when I did it for vector addition and scalar multiplication, and I really should have, but you can prove the commutativity of it, or for the scalar multiplication, you could prove that distribution works for it, doing a proof exactly the same way as this. A lot of math books or linear algebra books just leave these as exercises to the student because it's mundane, so they didn't think it was worth their paper. But let me just show you, I guess, the last property. Let me just say associativity, the associative property. That doesn't matter where. So let me show you. If I take some scalar and I multiply it times v, some vector v, and then I take the dot product of that with w, if this is associative the way multiplication in our everyday world normally works, this should be equal to, and it's still a question mark because I haven't proven it to you, it should be equal to c times v dot w. So let's figure it out. What's c times the vector v? C times the vector v is c times v1, c times v2, all the way down to c times vn. And then the vector w, we already know what that is, so dot w is equal to what? It's equal to this times the first term of w, so c v1 w1, plus this times the second term of w, c v2 w2, all the way to c vn wn. Fair enough. That's what this side is equal to. Now let's do this side. What is v dot w? Alrighty, here, v dot w, we've done this multiple times. This is just v1 w1 plus v2 w2 all the way to vn wn. I'm getting tired of doing this, and you're probably tired of watching it, but it's good to go through the exercises. You know, if someone asks you to do this now, you'll be able to do this. Now, what is c times this? So if I multiply some scalar times this, that's the same thing as multiplying some scalar times that. So now I'm just multiplying a scalar times a big, this is just the regular distributive property of just numbers, of just regular real numbers. So this is going to be equal to c v1 w1 plus c v2 w2 plus all the way to c vn wn. And we see that this is equal to this, because this is equal to this. Now the hardest part of this, I remember when I first took linear algebra, I found when the professor would assign, you know, prove this, I would have trouble doing it because it almost seems so ridiculously obvious that, hey, well, you know, obviously if you just look at the components of them, it just turns into multiplying of each individual component and adding them up, and those are associative. So that's obviously, so what's there to prove? And it only took me a little while. They just wanted me to write that down. You know, they didn't want something earth-shattering. They just wanted me to show when you go component by component, and all you have to do is assume, you know, kind of the distributive or the associative, the commutative property of regular numbers, that you could prove these same properties also apply in a very similar way to vectors and the dot product. So hopefully you found this reasonably useful, and I'll see you in the next video where we could use some of these tools to actually prove some more interesting properties of vectors.
ဟုတ်ပါပြီဒီဟာလည်းအမှန်မှန်နဲ့ရန်ခတ်တဲ့ concept တော့မဟုတ်ပေါ့နော်ဒီဟာသူ့မှာရှိတဲ့ properties လေးသူပြောပြတာဒီ properties တွေနာမည်လေးအားလုံးလို့ရင်းနှီးကြမယ်ထင်ပါတယ်ပေါ့နော် associative တို့ distributive တို့ commutative တို့ဟုတ် cumulative တို့ဒီဟာလေးရတယ်ဆိုဒီသူငယ်တန်းမဟုတ်ဘူးဒီအလယ်တန်းတို့အထက်တန်းထဲမှာလည်းကလုံးသင်ပြီးသွားပြီပေါ့နော်ဒီဟာလေးအရန်ခတ်တဲ့ဟာတော့မဟုတ်ပါဘူးညီမလေးတို့အကုန်လုံးလိုက်နိုင်မယ်လို့ယုံကြည်ပါတယ်လို့ဟုတ်သွားမင်္ဂလာပါကိုနောက်တစ်ခုသွားအောင်ဒီဟာ tutorial လည်းမပြောတော့ဘူးเนาะဒီဟာအားလုံးလို့သိပြီးသားလို့ဆိုတော့လေเนาะ
I have two non-zero vectors. Say the first vector is x, the second vector is y. They're both a part of, or a set, they're both in the set Rn, and they're non-zero. Non-zero. It turns out that the absolute value of their, let me do it in a different color. The absolute, let me do it in this color is nice. The absolute value of their dot product of the two vectors the absolute value, remember this is just a scalar quantity, is less than or equal to the product of their lengths. And we've defined the dot product, and we've defined lengths already. It's less than or equal to the product of their lengths. And just to push it even further, the only time that this is equal, so the dot product of the two vectors is only going to be equal to the length. So this, the equal and the less than or equal apply only in the situation, we write that down, only in the situation where one of these vectors is a scalar multiple of the other, or they're collinear. They're just, the one's just kind of a longer, shorter version of the other one. So only in the situation where, let's just say, x is equal to some scalar multiple of y. And these inequalities, or I guess this equality and this inequality, this is called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. So let's prove it, because you can't take something like this just at face value. You shouldn't just accept that. So let me just construct a somewhat artificial function. Let me construct some function of some that's a function of some variable, some scalar t. Let me define p of t to be equal to the length of the vector t times the vector, some scalar t times the vector y minus the vector x. As the length of this vector, this is going to be a vector now, is that squared. Now, before I move forward, I want to make one little point here. If I take the length of any vector, of any real vector, so the length of any real vector, I'll do it here. Let's say I take the length of some vector v. I want you to accept that this is going to be a positive number, or it's at least greater than or equal to 0, because this is just going to be each of its terms squared, v2 squared all the way to vn squared. All of these are real numbers. When you square a real number, you get something greater than or equal to 0. Then you sum them up, you're going to have something greater than or equal to 0. And you take the square root of it, the principal square root, the positive square root, you're going to have something greater than or equal to 0. So the length of any real vector is going to be greater than or equal to 0. So this is the length of a real vector, so this is going to be greater than or equal to 0. Now, in the previous video, I think it was 2 videos ago, I also showed that the magnitude or the length of a vector squared can also be rewritten as the dot product of that vector with itself. So let's rewrite this vector that way. So this is equal to, the length of this vector squared is equal to the dot product of that vector with itself. So it's ty minus x dot ty minus x. In the last video, I showed you that you can treat multiplication, or you can treat the dot product very similar to regular multiplication when it comes to the associative, distributive, and commutative properties. So when you multiply these, you can kind of use these multiplying these 2 binomials. You can do it the same way as you would just multiply 2 regular algebraic binomials. You're essentially just using the distributive property. So but remember, this isn't just regular multiplication. This is the dot product we're doing. This is vector multiplication, or one version of vector multiplication. So if we distribute it out, this will become ty dot ty. So let me write that out. That'll be ty dot ty. And then we'll get let me do it this way. Then we get the minus x times this ty. So you get, or instead of saying times, I should be very careful to say dot. So minus x dot ty, and then you have this ty times this minus x. So then you have minus ty dot x, and then finally you have the x's dot with each other. And you can do them as minus 1x dot minus 1x. So you can say plus minus 1x, right? I could just say, do this as plus minus 1, or plus minus 1. So this is minus 1x dot minus 1x. So let's see. So this is what my whole expression simplified to. or expanded to. I can't really call this a simplification. But we can use the fact that this is commutative and associative to rewrite this expression right here. This is equal to y dot y times t squared, right? T is just a scalar, minus, and actually this is 2. These two things are equivalent, right? If they're just rearrangements of the same thing, and we saw that the dot product is associative. So this is just equal to 2 times x dot y times t, and I should do that in maybe a different color. So these two terms result in that term right there. And then you have if you just rearrange these, you have a -1 times a -1, they cancel out, so those become plus, and you're just left with plus x dot x. And I should do that in a different color as well. I'll do that orange color. So those terms end up with that term right there. And of course, that term results in that term. And remember, all I did is I rewrote this thing and said, look, this has got to be greater than or equal to 0. So I can rewrite that here. This thing is still just the same thing. I've just rewritten it. So this is all going to be greater than or equal to 0. Now let's make a little bit of a substitution just to clean up our expression a little bit. And we'll later back substitute into this. Let's define this as A. Let's define this piece right here as B. So the whole thing, -2x dot y. I'll leave the t there. And let's define this, or let me define this right here as C, x dot x as C. So then what does our expression become? It becomes A times t squared minus, I want to be careful with the colors, B times t plus C, and of course we know that's going to be greater than or equal to 0. It's the same thing as this up here, greater than or equal to 0. I could write P of t here, P of t. Now this is greater than or equal to 0 for any t that I put in here, for any real t that I put in there. And so I could just put in, let me just pick a t to be, let me evaluate our function at b over 2a. And I can definitely do this, because what was a? I just have to make sure I'm not dividing by 0 anyplace. So a was this vector dotted with itself. And we said this is a non-zero vector. So this is the square of its length. It's a non-zero vector, so some of these terms up here would end up becoming positive when you take its length. So this thing right here is non-zero. If this is a non-zero vector, then 2 times the dot product with itself is also going to be non-zero. So we can do this. We don't have to worry about dividing by 0 or whatever else. But what does this be equal to? This will be equal to, and I'll just stick to the green. It takes too long to keep switching between colors. This is equal to a times this expression squared. So it's b squared over 4a squared. I just squared 2a to get 4a squared, minus b times this. So b times, this is just regular multiplication, b times b over 2a. I just write regular multiplication there, plus c. And we know all of that is greater than or equal to 0. Now, if we simplify this a little bit, what do we get? Well, this a cancels out with this exponent there, and you end up with a b squared right there. So we get b squared over 4a minus b squared over 2a, that's that term over there, plus c is greater than or equal to 0. And let me rewrite this. I could, if I multiply the numerator and the denominator this by 2, what do I get? I get 2b squared over 4a. And the whole reason I did that is because to get a common denominator here. So what do you get? You get b squared over 4a minus 2b squared over 4a. So what do these two terms simplify to? Well, the numerator is b squared minus 2b squared. So that just becomes minus b squared over 4a plus c is greater than or equal to 0. These two terms add up to this one right here. Now, if we add this to both sides of the equation, we get c is greater than or equal to b squared over 4a, right? It was a negative on the left-hand side. If I add it to both sides, it's going to be a positive on the right-hand side. So we're approaching something that looks like an inequality. So let's back substitute our original substitutions to see what we have now. So where are my original substitutions that I made? It was right here. So what was, and actually just to simplify it more, let me multiply both sides by 4a. And once I said, I said a, not only is it non-zero, it's going to be positive. This is the square of its length. And I already showed you that the length of any vector in any real vector is going to be positive. And the reason why I'm taking great pains to show that a is positive is because if I multiply both sides of it, I don't want to change the inequality sign. So let me multiply both sides of this by a before I substitute. So we get 4ac is greater than or equal to b squared. There you go. And I remember, I took great pains. I just said a is definitely a positive number because it is essentially the square of the length. Y dot y is the square of the length of y, and that's a positive value. It has to be positive. We're dealing with real vectors. Now let's back substitute this. So 4 times a, 4 times y dot y. Y dot y is also, I might as well just write it there. Y dot y is the same thing as the magnitude of y squared. That's y dot y. This is a. Y dot y, I showed you that in the previous video. Times c. C is x dot x. X dot x. Well, x dot x is the same thing as the length of vector x squared. So this was c. So 4 times a times c is going to be greater than or equal to b squared. Now what was b? B was this thing here. So b squared would be 2 times x dot y squared. So we've gotten to this result so far. And so what can we do with this? So, oh, sorry, this whole thing is squared. This whole thing right here was b. So let's see if we can simplify this. So we get, and I'll switch to a different color, 4 times the length of y squared times the length of x squared is greater than or equal to, if we square this quantity right here, we get 4 times x dot y, 4 times x dot y times x dot y. Actually, even better, let me just write it like this. Let me just write 4 times x dot y squared. Now we can divide both sides by 4. That won't change our inequality. So that just cancels out there. And now let's take the square root of both sides of this equation. So the square roots of both sides of this equation, these are positive values. So the square root of this side is the square root of each of its terms. That's just an exponent property. So if you take the square root of both sides, you get the length of y times the length of x is greater than or equal to the square root of this. And we're going to take the positive square root. We're going to take the positive square root on both sides of this equation. That keeps us from having to mess with anything on the inequality or anything like that. So the positive square root is going to be the absolute value of x dot y. And I want to be very careful to say this is the absolute value because it's possible that this thing right here is a negative value. But when you square it, you want to be careful that when you take the square root of it, that you stay a positive value because otherwise you have to, when we take the principal square root, we might mess with the inequality. So we're taking the positive square root, which will be, so if you take the absolute value, you're ensuring that it's going to be positive. But this is our result. The absolute value of the dot product of our vectors is less than the product of the two vectors' length. So we got our Cauchy-Schwarz inequality. So we got our Cauchy-Schwarz inequality. Now, the last thing I said is, look, what happens if x is equal to some scalar multiple of y? Well, in that case, what's the absolute value? The absolute value of x dot y, well, that equals what? If we make the substitution, that equals the absolute value of c times y, that's just x dot y, which is equal to, just from the associative property, it's equal to the absolute value of c times, we want to make sure our absolute values keep everything positive, y dot y. Well, this is just equal to c times the magnitude of y, or the length of y squared. Well, that just is equal to that is just equal to the magnitude of C times or the absolute value of our scalar C times our length of Y times our length of Y times our length of Y. Well, this right here, this, I can rewrite this. I mean, you can prove this to yourself if you don't believe it, but this, we could put the C inside of the magnitude, and that could be a good exercise for you to prove, but it's pretty straightforward. You just do the definition of length, and you multiply it by C. This is equal to the magnitude of CY times, the length of CY times the length of Y. Length of Y. I've lost my vector notation someplace over here. There you go. Now, this is X. So this is equal to the length of X times the length of Y. So I showed you kind of the second part of the Cauchy-Schwarz inequality, that this is only equal to each other if one of them is a scalar multiple of the other. And if you're a little uncomfortable with some of these steps I took, it might be a good exercise to actually prove it. For example, to prove that the absolute value of C times the length of the vector Y is the same thing as the length of C times Y. Anyway, hopefully you found this pretty useful. The Cauchy-Schwarz inequality we'll use a lot when we prove other results in linear algebra. And in a future video, I'll give you a little more intuition about why this makes a lot of sense relative to the dot product.
ဟုတ်ပါပြီဒီ lesson ကနည်းနည်းလေး theorem ကို proof လုပ်သွားတာများတယ်ပေါ့နော်အရင်လည်းကောင်းစားနေပေါ့ဒီကဘာမှ trade မဟုတ်တော့ proof လုပ်တာဖြစ်တဲ့အတွက်နည်းနည်းပေါ့ proof လို့လုပ်တယ်ဆိုတော့ကိုလိုက်ကြည့်ရဆိုသဘောလေးပဲပေါ့နော်အရင် trade ကောင်းဖြစ်ပါနဲ့တော်တော်များလေးကဒီခုနကပြတ်သွားမယ်နော်သမီးရပြောင်းလိုက်တယ်တော်တော်များများကသူပြောတဲ့ဒီပထမအောင်သူပြောတဲ့ဟာကိုဒီမှာအဲ့ဒါဆိုသိပြီးရ associative role တို့ဒီ community role အဲ့ဒါတွေနဲ့ပတ်သက်ပြီးပြန်ပြီးသူပြောလိုက်တယ်ဆိုတဲ့သဘောပါပဲ trade တော့မဟုတ်ပေါ့နော်အရင်ကောင်းစားတဲ့ဒီဟာခဏနားထောင်အောင်တော့တွေရောက်တော့ဒါပေမဲ့ကြည့်နားလဲကိုနားလဲလို့ပဲကိုလက်ခံလိုက်ပေါ့အရင်လည်းကောင်းဖြစ်နေဒီဟာဟုတ်ပြီလားနောက်တစ်ခုသွားအောင် better triangle ဒီမိနစ်လဲနည်းနည်းများနေပြီတော်တော်ဒီနေ့ဒီမောက်ရရအောင်နည်းနည်းလေးကောင်းနေမှာတော်တော်လေးရှုပ်နေပြီသူပြောတဲ့ဟာတွေနည်းတင်ချာတွေပဲများနေပြီကောင်းမှုနေပြီမလေးညီမလေးတော့မသိရဲဆိုတော်တော်လေးမှုနေပြီပေါ့နော်โอเคဒီနေ့ဒီမောက်ရရအောင်လို့နော်သူကဒီမှာ16မိနစ်ဆို16မိနစ်နောက် brain မနိုင်တော့နောက်16မိနစ်မနိုင်တော့အောင်နောက်ကโอเคအားလုံးပဲ bye bye ပါခဏနော် let's stop လုပ်လိုက်အောင်